In this section, I'm going to formally introduce the Fourier series representation for periodic functions, and I'm also going to show how we can find the Fourier series representation for a given periodic function. Before I can formally introduce Fourier series, I first need to introduce some related terminology. And the first term that I need to introduce is the term harmonically related. So we can talk about a set of complex sinusoidal functions as being harmonically related. So just reading the definition from the top of the slide, a set of complex sinusoids is said to be harmonically related if there exists some constant omega naught such that the fundamental frequency of each complex sinusoid is an integer multiple of omega naught. So for example, this set of functions, which is denoted by phi subscript k for various integer values of k, these functions are harmonically related. The reason why is if we look at the fundamental frequency of these complex sinusoids, which are k omega naught, they're all integer multiples of the same frequency omega naught. Therefore, these functions are harmonically related. Now you can show that if you take a linear combination, in other words a weighted sum of harmonically related complex sinusoids, the function that you end up with for the result of the sum is periodic. And in particular, for the set of complex sinusoidal functions that we have here on the slide, these phi subscript k, if we take a weighted sum, in other words a linear combination of these complex sinusoids, you can show that the period of the function that you end up with is 2 pi over omega naught. At this point, I can finally introduce the formal definition of a Fourier series. So again, a Fourier series is a representation for periodic functions. So suppose that we have a periodic function x, which has the fundamental period capital T, and the fundamental frequency omega naught, which by definition is equal to 2 pi over t. It turns out that x can be represented as a linear combination of harmonically related complex sinusoids. In other words, x can be written in terms of a summation of this particular form that I've highlighted. This summation is referred to as a Fourier series. It's a Fourier series representation of our periodic function x. The ck, this coefficient sequence that appears in the summation, is referred to as the Fourier series coefficients for the function x. And overall, this formula that involves x and the right-hand side, which involves the Fourier series, this is sometimes referred to as the Fourier series synthesis equation. The word synthesis is chosen simply because if we know the Fourier series coefficients, in other words, if we know these coefficients ck, we can use them to synthesize or reconstruct the original signal x by computing this sum on the right-hand side. We can also group terms in pairwise in this summation. So we can take terms that have plus and minus the same index value. By index value, I'm referring to this index of the coefficients sequence c. So we can choose the coefficients that have the indexes plus capital K and minus capital K and group them together into what are called the kth harmonic components of the signal x. And both of these components have the same fundamental frequency, k omega naught. Then lastly, as a matter of notation, sometimes we want a convenient way to say a particular function has a particular set of Fourier series coefficients. And this is exactly what this notation here does. What's on the left side of the double arrow is a function, and then what's on the right side of the double arrow is a sequence. So it's saying that the function x has the coefficient sequence, the Fourier series coefficient sequence, c. As we'll see later, Fourier series are useful for quite a number of purposes, but for the moment I'll just ask that you give me the benefit of the doubt that Fourier series are actually useful for something. And if you're willing to buy into that, then a natural question to ask is, if you're given a periodic function x, how do you find its Fourier series representation? In other words, how do you find its Fourier series coefficients? And this is essentially what this slide is dealing with. So suppose that I have a periodic function x with the fundamental period capital T and the fundamental frequency omega naught, which by definition is equal to 2 pi over t. And we want to find the Fourier series coefficients, which are denoted by the ck here. We can do this using the formula that's stated here. This is a formula for computing the kth Fourier series coefficient for the function x. And this equation is sometimes referred to as the Fourier series analysis equation. The word analysis comes from the fact we're taking our original function x and we're analyzing it or studying it to determine what its Fourier series coefficients are. Now I need to make one other comment about this equation here because there's probably some mathematical notation that you're not familiar with. in particular with respect to this integration operation here. This is not a typo, that it's not missing an upper limit for the integral, and this t that appears here is not a lower limit of integration either. Essentially what this notation denotes, where we have just a single subscript on an integral, this is saying we're integrating over an interval of this length. So it means we're integrating over an interval of length capital T. And the context where this is typically used is where the function that you're actually integrating is periodic, and the period is basically capital T. In other words, you're integrating a periodic function over a period of that function. And when you're doing such an integration, it doesn't matter what you choose for the lower limit and upper limit specifically. All that matters is the length of the interval. In other words, the difference between the upper and lower limit. So we just denote this by a single subscript. So again, this just means we're integrating over an interval length capital T, and it turns out this function here is periodic with period capital T. This is because x by assumption is periodic with period capital T, and also this complex sinusoid is also periodic with period capital T. So when you multiply them together, you get a function which is periodic with period capital T. At this point, I'd like to consider a couple of examples to illustrate how we can make use of the Fourier series analysis equation that's introduced on this slide. And in particular, I'd like to start with example 5.1. In this example, we're given the periodic function x, which is shown plotted in this figure here, where capital T denotes the fundamental period of this function, and we're asked to find the Fourier series representation of this function x. So the way we go about doing this is using the Fourier series analysis equation. So this is the equation that's given on this particular line. And in order to use this equation, we need to identify the fundamental frequency of the function x, which is denoted by omega naught here. And we also need to choose an interval of length t to integrate over. So with respect to omega naught, this is simply going to be equal to 2 pi over capital T by definition. So that's easy enough to find. For the interval we're going to integrate over, in principle there's infinitely many choices that you can make. Only a relatively small number that would probably make sense. And it turns out not really to matter too much which one we choose of some of the ones that would make the most sense, like 0 to t, minus t to 0, or minus t over 2 to t over 2. Typically these would be the ones that you'd most likely want to choose. It turns out not to really matter too much for the purposes of this example. So I'm just going to choose to integrate from 0 to t over this interval here. In other words, in terms of the diagram, I'm integrating from 0 on the left over to capital T on the right. This is clearly an interval of length capital T. So given that I'm integrating over this range here, this means that the function that I'm integrating is either equal to plus a or minus a. It's equal to plus a between 0 and t over 2 in this range here, and between t over 2 and t the function is equal to minus a. So when I substitute in for x into this formula here, I'm going to be plugging in the value of capital A between 0 and t over 2, and I'm going to be plugging in the value of minus a between t over 2 and t, or I should say capital T over 2 and capital T. So this gets me to this next line here. I've just substituted in the function x. And then what we can do next is we can actually perform the integration. So if we integrate the function, assuming that k is not equal to 0, what we're going to get is just another exponential function. When I integrate this exponential, I get another exponential, which is this first term here. When I integrate the second integral, again, assuming k is not equal to 0, I'm just going to get another exponential function, which is this one here. And then we just need to simplify this expression further for k not equal to 0. But of course k might be equal to 0. In this case what happens is that this exponential effectively disappears and just becomes, because it becomes e to the 0, which is 1. So effectively the exponential just drops out, and all we're left with is just a function that's a constant equal to capital A. And similarly in the second integral here, in the case that k is equal to 0, this exponential just gets replaced by 1, and what we're left with is just minus a, so it's a constant function. So in these cases, because we're integrating a constant function, we get a much simpler result for the integration. So we need to further simplify this case as well for k equal to 0. So this is what remains to be done, is we need to simplify the expressions that we have for the case k not equal to 0 and k equal to 0. So at this point I'm just going to scroll the solution up so we can see the next part of it. So first I'm going to focus on simplifying the answer for the case k not equal to 0. So I'm going to consider simplifying this expression here, the one that's for k not equal to 0. So if I just copy this formula down below, so this is the same formula or same expression, I need to simplify this. So I can pull some constants out, factor some constants out of the outermost pair of brackets here. And also, in going from this line to the next one, I'm using the fact that t times omega naught equals 2 pi. Remember that omega naught is equal to 2 pi over capital T, so what we really have here is t times 2 pi over t, but the t's cancel and you're left with 2 pi. So this is where this 2 pi is coming from. We're getting a t times an omega naught, which is giving us a 2 pi here. And then we can do some very basic algebraic manipulation to get from this line here to the line at the bottom of this page here. And at this point we can observe that e to the minus j pi is actually equal to minus 1. So we can replace this highlighted expression by minus 1. And similarly we can observe that e to the minus j2 pi is just a constant equal to 1. So we can replace this highlighted expression with 1, which gives us this next line down here. Now I need to scroll the solution up so we can see the last part of the solution. So continuing from where we left off, which was on this line here, we can do some basic algebraic manipulation to get from this line down to this line here. And the quantity in square brackets we can simplify further by observing that we get one of two results for the quantity in square brackets depending on whether k is even or k is odd. In the case that k is odd, we're going to get minus 1, which is minus 2. In other words, we get this result here. In the case that k is even, we get 1 minus 1, which is 0 for the quantity in square brackets. So we can substitute this result in here for minus 1 to the k minus 1, in other words for the quantity in square brackets, which gives us this next line. And because we're excluding the case that k is equal to 0 in this particular analysis that we're doing here, this is the reason why we have this constraint that k is not equal to 0. So this gives us the answer for ck in the case that k is not equal to 0, but we still have to consider the case that k is equal to 0. So if we copy the formula from earlier in this example, what we had for the result that k is equal to 0, this is what we had from earlier, and we just needed to simplify this expression further. So just using basic algebra, if we simplify this, it turns out that everything cancels and we get a result of 0. So C0 is equal to 0. So if we combine these results together, so the result for k not equal to 0 and the result for k equal to 0, we end up with this result here for the coefficient values ck. So our Fourier series representation for x is given by this formula here, where ck, in other words the Fourier series coefficients, are chosen according to this result here. The next example that I'd like to consider is example 5.3. In this example, we're given the periodic function x with fundamental period capital T equal to 3 as shown in figure 5.3, so this figure here. So essentially what we have is a periodic impulse train. And what we're asked to do is we're asked to find the Fourier series representation of x. So effectively we're being asked to find the Fourier series coefficients for the function x. To find the Fourier series coefficients, we simply use the Fourier series analysis equation, in other words this equation here. But in order to use this equation, we have to identify what omega naught is, so what's the fundamental frequency of our function x. And we also have to select a particular interval to use for our interval of length capital T. So with respect to the choice, or the value for omega naught is by definition just equal to 2 pi over capital T, and we're told capital T is equal to 3 in this problem, so we have 2 pi over 3 for omega naught. And then with respect to the choice of our interval to integrate over, in other words, which particular interval of length t should we choose, well, from the point of view of correctness, it doesn't matter. No matter what interval we choose, we'll get the same answer. However, different choices of interval may lead to an easier solution to simplify. So the general advice that I would give is when you're trying to find the Fourier series coefficients of a function and that function happens to have symmetry, either it's even or odd, it's often advantageous to choose the interval to be centered about the origin. So in this particular case, I'm choosing the interval to be from -3/2 to +3/2. In other words, it's centered about the origin. Clearly this interval is of length 3, which is what's required here, so it's of length capital T. So now we're set to actually start using the formula. The first thing we're going to need to do is we're going to need to substitute in for x, the actual expression that we're integrating. So in this particular case, we're integrating from -3/2, which is here in the graph, to +3/2, which is here. In other words, we're integrating over the range that's indicated by this double-ended arrow here. It's an interval of length 3. And over this interval, what we see in terms of the function we're integrating is we have a delta function that's shifted by 1, and we have a delta function that's been shifted by -1 and then multiplied by -1. So this gives us the two terms that appear here. The second term is our delta function that's been shifted by +1, and then the first term is the delta function that's been shifted by -1 and then multiplied by -1. So what we do next is we take and split the integral into two separate integrals, one where we're dealing with this term here and one where we're dealing with this term. So if we look at the first integral we have on the next line, we can make an observation about the integrand. This integrand here is always equal to 0 outside of the range we're integrating over. So when we're integrating from -3/2 to +3/2, outside of this range the integrand is always 0. The reason that this is important is because we can replace these limits with plus and minus infinity and it won't change anything, because we're just adding in an extra area of 0, but adding 0 doesn't change anything. And this is helpful because once we change these limits to plus and minus infinity, we can use the sifting property to evaluate the integral. And what we'll get from the sifting property is we'll end up with everything that's not this shifted delta function evaluated at the point where the shifted delta function is non-zero. So what we're going to end up with is the whole integral just collapses into this expression here plus the minus sign out front, evaluated at t equal to -1, because this is the place where the shifted delta function is non-zero. So this gives us this term on the next line. And then we do a similar thing for the other integral. We can make the observation that the integrand in the second integral is always equal to 0 outside of the range that we're integrating over. Therefore, we can change these limits to be plus and minus infinity and it won't change anything. And once these limits are changed to plus and minus infinity, we can now use the sifting property to evaluate the integral. And the sifting property effectively says that this whole integral is going to collapse to just this particular expression here, our exponential, evaluate it for the value of t where the shifted delta function is non-zero. In this case, it's going to be for t equal to 1. So this whole integral just collapses into this highlighted expression, the exponential part, at t equal to 1. So that gives us this second term here. And then of course we can do some basic algebraic manipulation to get us down to this line, or I should say to this line here. At this point we can observe that what we have, this highlighted expression in the square brackets, this is effectively up to a scale factor, a sine function. In particular, it's just 2j times sine of minus 2 pi by 3 times k. And we're just using Euler's relationship here, with the fact that sine theta is equal to 1 over 2j e to the j theta minus e to the minus j theta. So we're just using this relationship here to rewrite this pair of complex sinusoidal terms as a sinusoidal function. And of course we can get from this line to the very last line by observing that the sine function is odd, so we can essentially pull this minus sign out front like this, and this gives us our final answer for the expression for ck. And of course once we have our expression for ck, we can then, if I scroll this up so we can see the remainder of the solution, we just take the ck value that we've computed, which is this expression here, and we can substitute that in for ck in the Fourier series summation, which gives us our final answer. So this is our Fourier series representation of the function x.